Welcome to Complex Numbers Part 2. Have a look around the screen, some interesting stuff going on there. What's this bar over all the numbers here? What's that mean? Well, here they are, all over stuff. Oh, what's it doing there? Well, come up here, and of course, it's about the conjugate. And that's where we left off the last presentation. How do complex numbers hide in a real quadratic equation? And the idea is that they occur as conjugate pairs like this, and we now have a symbol for that. We call it Z bar. Z with a bar over the top is the complex number with the opposite sign between real and imaginary parts. And why did we look at them before? Well, the coefficients of a quadratic equation involve the sum and the product of the roots, and so this comes to 2a, the bi's cancel out, and so the sum is real. A and b are real in the complex form, and this is a squared take b squared I squared, which is also real, a squared plus b squared. So that's why they're special. They have a sum and a product, both real, so they can hide in that quadratic equation. You can't see that they're complex roots till you go to work it out. Okay, so what we're going to do, coming around the screen, we're going to look at all the properties of these because they are interesting pairs of complex numbers. But have a look in here. What's going on there? Study it carefully. What do you notice? Hey, there's no x and y axis now. It's real and imaginary. So that suggests that we're going to plot complex numbers. Looks like it. That'll be in a later presentation. Our whole focus here is about showing results for conjugates, pairs of numbers with the opposite sign between real and imaginary part. So let's go down and start looking at that and see if we can see some patterns. So first of all, there's our definition. Screen clippings here from Hayes and Harris publications. So if z equals a plus bi, the conjugate of z is what we refer to here as the same real imaginary part with the opposite sign in between. Okay, now we have a symbol for it, so we need to remember that one. All right, let's go down and start looking at some properties. Here are the properties, and we're going to set about proving some of these. Okay, the conjugate of a conjugate takes it back to the original complex number, does it? So if z equals a plus bi, the conjugate would be a take bi. The conjugate of the conjugate, opposite sign again. Oh, gee, that's true. Back to z. So we put these implied sign here. Oh, well, that's interesting. Usually if we do a little proof like that, we put as required, don't we? That's important. Well, these others, the conjugate of a sum is the sum of the conjugates. The conjugate of a difference is a difference of the conjugates. Hey, this is pretty commonsensical. It's easy to remember these. It's just what you'd like to happen. The conjugate of a product of the conjugates. Conjugate of a quotient of the conjugates, provided that you're not dividing by zero there. Is zero a complex number? Do you remember the question I left you with at the end of the last part of part one of complex numbers? Was what's the relationship of the two sets? Well, real and complex. Well, of course, complex numbers, imaginary numbers, are the bigger set because the real are the complex numbers with no imaginary part. So the complex number z2 could be some number plus naught I, or it could be naught plus naught I. And that would just be zero. So reals are complex with no imaginary part, aren't they? So you could think of it like that. What about this result down here? The conjugate of a power of a complex number is you can find the conjugate first and then take the power of it. So nice and easy rules. We've got to establish those and start working with them so that we can investigate these complex conjugates, important pairs, in more detail. So here's another screen clipping from Hayes and Harris publications. We were going to try and show that the conjugate of a sum is the sum of the conjugates for all complex numbers. So because we want to do it for all complex numbers, we have to have a general form for each one, not a particular pair. So we're going to say let Z1 be A plus BI and Z2 be C plus DI. First thing we want to do working with conjugates is find the conjugate of the two. So we see the opposite sign in here between real and imaginary parts. Now writing down the sum, well, the sum of the two, well, we could have put another line in there, A plus BI plus C plus DI. So you'll add the imaginaries, add the reals and add the imaginaries for the sum there. So I left out that step really. The step might have been nicer to put this first, like that, and then collect up your terms. Okay, the conjugate of that is the opposite sign between them. And then if we repair them here, so this is neg BI, so A plus C take BI and take DI, and then pair them up, A take BI and C take DI. So this is the conjugate of Z1, this is the conjugate of Z2, and that's as required. Alright, so get the idea. This is the important step up here, where because you're doing a proof or a show that, you have to let Z1 and Z2 be general expressions for complex numbers, not particular cases. Alright, come down and I'll get you to do some here. Can you do this first one here, letting Z1 equal A plus BI, Z2 equal C plus 2A, and do it the same way. This one here is using the properties that we just had a look at, so you might have to rewind the presentation, just toggle back and have a look at the rules. What are you allowed to do with a conjugate of a difference of two complex numbers? Okay, and then simplify it. All right, this one here is back to letting Z equal A plus BI and tracking through the relationships there. So pause the presentation and have a go at those problems. I'm going to show you the work solutions in a minute. Here we go. I'll take you down now. Here are our work solutions. Just look at the setting out and remembering things like as required here. Makes the finishing touches, puts the finishing touches on any proof or show that. All right, let's go on and develop this a little bit further. Here's another little proof, proving that the conjugate of a product is a product of the conjugates. Okay, so Z1 is A plus BI again, because it's a proof or show that. C plus DI, let's multiply them together. AC by ADI, those two, BCI and BDI squared. And BDI squared is neg BD. So collecting up your real parts, AC take BD, and the I terms, AD plus BC. So the conjugate of that product now has the opposite sign in there, like that. And we could now go and check out the product of the conjugates, see if they're equal. And this is now A take BI by C take DI, and multiplying them all out, AC, neg ADI, neg BCI, plus BDI squared, which is going to be neg BD again, because I squared is neg 1. And just collecting these up, let's put the negative out the front, so it's AD plus BC. What's that sign there? Because neg by a positive will give you neg BI there, BCI. Okay, so what do you notice? Yep, this line and this line are the same. So we've got that, and as required would be nice in there. All right, do you want to do some? Okay, come and have a look at the next set of exercises here, some more proofs. I want you to pause the presentation and work your way through in the same way. Okay, and then I'll show you the answers. All right, I'll show you the last question here, number 8. There we are. I think it's important to do all of these to get familiar with the conjugates and their properties. Okay, I'll show you the answers Okay, almost. Hang on, let's just go here a little bit more. Question 4. Just check it out. Okay, let's go to question 5 and 6. I think we can fit those on. And 7 and 8. 7's on there. And 8. All right, let's go on. How are you going? Getting the hang of it? Some of it's fairly tricky, but you've just got to watch yourself. Now, conjugate generalizations. What does generalization mean? It means to extend it for all n. That symbol means for all n. In other words, can you keep it going? We said that in this first one here, that the conjugate of a sum of two complex numbers, oops, it's not the conjugate of a conjugate there, so let's do that again, z1 plus z2, you could do it to each part. Can you take that further? Would it work for 3? Would it work for 4? So this conjugate generalization is a way of reaching bigger n through a process. Let's look at the process. So let's take the next case. So this is a 2. So this is case n equals 2. Let's take case n equals 3. The first thing we might do is consider this as a conjugate of a sum. Right? Let's have a look now. I've left this step out. I'd like you to do this next. This equals the conjugate of thinking about the complex number as a sum of 2. So this is what they're saying here. Think of it as that one plus that one. And then you're allowed to say, split, first of all, split it as conjugate of z1 plus z2 plus conjugate of z3. That's a mistake there. That should be a 3 there. And that's case n equals 2, isn't it? You're allowed to split them. So as soon as you do this, you're allowed to split it into the conjugate of that plus the conjugate of that. And then, of course, you can split z1 plus 2 down there because we know this rule, case n equals 2. So the idea is to establish something that is correct, and we've proven that before, and then to use it. Let's look at the 4 one here. Now, the idea would be if it's a conjugate of 4, let's think about it as that complex number plus this one. Because you know if you have 2, just 2, it's a conjugate of the first one plus the conjugate of the second. So it's a bit of a tricky do there. Now, can you break this down? Yes, because you proved it from up there. Okay, so case 4 links closely to case 3. And the idea is to have, what? An identical pattern continuing. Got to show an identical pattern can keep going, so every n is covered. So you could keep it going right up to here. Okay, so that again, if you can show that this leads to this, leads to this, then it's irrefutable that the pattern will just roll on. So that's not a bad way of doing it. Roll on. The pattern must be shown to roll on. You must have an identical linkage so that people can see that it will never stop and you can get for all n. Okay, this is called the process of mathematical induction. It's called the process of mathematical induction. There's also the principle, and this is spelled incorrectly here. It should be principle. That's principal of a school, the main person. It should be LE for the rule. The principle of mathematical induction is a more formal treatment, and usually do that later on in university, as the book's saying here. But what we're going to do in a later presentation is have a look at both of them, because this type of proof is very important for generalizations. Come back up here. Whenever you see a pattern in any area, and we're going to do this in polynomials as well later on, when you see a pattern in any area for a particular case and say, well, can I extend it for more and more of the values, or for n, generalize it for all n, then this method, the process of mathematical induction, which is in the course, or using the principle of mathematical induction, is a powerful tool. All right, come down and let's see how we might do something here. So I want you to try and do the same thing. Assuming the conjugate of a product is a product of the conjugates, we've already proved that. Explain why, or just show that maybe, I like show that better, show that you can get the conjugate of n, a case n equals 3, where there's 3 complex numbers. Just remember what we did. We divided up into 2 and showed the same pattern. And then I want you to do the same way, the same pattern must flow on. Same pattern, rolls on. Okay, so when you break this one up, you'll use the same idea. Okay, because that's the only way people are going to believe it's going to keep going for all n. It is a proof. And you might say, well, Huddy, how is it by induction? Isn't induction using examples? Yes, it is, but the idea is the examples are n equals 2, not particular examples in complex numbers. We're rolling on this way, and why the inductive process for 2 leads to 3 leads to 4 is our proof must show the algebra is always the same. That is, there's a common pattern, and then the process of induction, one value after the other, can be achieved. All right, I want you to try these problems, and I'll show you the solutions now. So there they are. Okay, how did you go? Let's go on, and I like to put case n equals 2, etc. up here, but I'll show you that in a minute. Okay, let's go on, and I want to give you Huddy's version of proof by the process of mathematical induction. Okay, now the first step is you must prove the proposition true for the starting value, which is usually, in this one, in complex numbers, n equals 2. Because you really are usually starting with, okay, I've got 2 of them, and I'm going to show that this is true, and then I want to extend it for all n. So you must absolutely prove case n equals 2, which we've been doing. This means a strict proof for the value n equals 2. That is, let z equals a plus bi, and then c plus di, and start to establish. So we establish our result. And now the next case builds on that. You show how to use a step, a common step. It's called the inductive step. And you must repeat that. You must show an identical connection, because we want a pattern which we can irrefutably say rolls on, irrespective of how many times you do it, so you'll reach all n. Okay, so the common step up there was to introduce the idea that the sum of more complex numbers could always be considered as the sum of 2 and then breaking it down. Okay, now you do this usually once up here and then twice more to establish the pattern, because we need it to be shown to be able to be rolled on there. Okay, I'm going to do an example and get you to do one. Indicate the pattern observed by, this is your setting out of the connection going on from one to the other, and I'll show you that. And you must make this statement, continuing the inductive process, and then show the case for n equal 1 connects to case for n using it. This is optional. Okay, now up above, what it would mean is, I like students to do this, z1 plus z2 up to zn equals, here, the conjugate of z1 plus up to zn take 1, making that 2 again, plus zn, which is the conjugate of z1 up to zn take 1 plus the conjugate of zn, and then write the result. So showing the same sort of pattern each time. Now you don't actually have to do this in this course. but I think it's a good idea to show ultimately that the nth case will be able to be attacked with the same splitting of terms. And therefore, at the end, when you've done that and made this statement that it's true for n, even without this, you make the statement, therefore true for n greater than or equal to 2 by the process of mathematical induction. Okay, you should make that formal statement. It's a more casual type of proof than by the principle of mathematical induction, but it still is a proof and should have a mathematical precision to it. Right, do you want to come and do one? Okay, well, let's come and do one. Here we are. Okay, here we are. Prove the conjugate of the sum is the sum, let's see this conjugate. Well, you've got to do more here. So, go z1 plus z2 up to zn equals right up to zn for all n greater than or equal to 2. You've got to have 2 to do the first sum. All right, so the proof then is you must start with the lowest case. So here, start case n equals 2, and this has got to be a strict establishment of the rule for the first case, and then show that the rest can be achieved by flowing on of that pattern. So here we go. Let z1 equal a plus bi, z2 equals c plus di. So now, case n equals 2, conjugate of z, we'll just do z1 plus 2, z2 will build it. z1 plus z2 is, we've done this before, a plus c plus b plus di. But the conjugate of that sum is a plus c, take b plus di, and this was an example from the textbook. And if we regroup this, a plus c take bi take di, which is a take bi, we'll just package them up like this, plus c take di, which is equal to the conjugate of z1 plus the conjugate of z2 as required. Therefore, true for case n equals 2. Okay, so that's a strict formal starting proof. So we've got something to use as a tool to build and to roll the pattern on for other values. Okay, let's do case n equals 3. So that's the conjugate of z1 plus z2 plus z3, which can be thought of as the conjugate of this one as a single complex number plus this one, which is therefore the conjugate of z1 plus z2 plus the conjugate of z3, and that's splitting two terms, splitting it into two terms and then applying the rule that we just established strictly, case n equals 2. And then we can use case n equals 2 again, because there are two terms within this one. So put that case n equals 2 used twice there. Therefore, true for case n equals 3. You see what we're doing? We're just going to keep this rolling on. Case n equals 4. So here the conjugate of z1 plus z2 plus z3 plus z4 equals the conjugate of z1 plus z2 plus z3 plus z4. See what I'm doing? Same pattern. Is the conjugate of this one using case n equals 2, because I'm considering that first line as those two terms. So I'm applying case n equals 2. And then I can break this from what I've established for case n equals 3. And what I'm doing there is applying that case n equals 3 from up here. Okay, can you see I'm starting to develop a pattern, because I must establish the pattern rolls on for all n. Must establish it. It must be the same way every time. Now, case n equals 5. Some people argue that that's enough up there, but I think you should do it with three cases or inductive steps. It's called the inductive step, where you're using the same way of getting to the next value as you did for the previous ones. So this is the conjugate of this one up to 4 plus this one, and that's case n equals 2, and then this one can be split because it was already established here, and the reason for doing that is case n equals 4 from before. So therefore, oops, left it out here, therefore true for case n equals 4. Same thing here, therefore true for case n equals 5. Okay, so I think we've established a good pattern. Okay, so we can now say, continuing the inductive process. Okay, continuing the inductive process, what are we going to do? We can say here Z1 plus Z2 up to Zn equals Z1 plus Z2 right up to the one before n take 1, plus Zn equals this one, Z1 plus Z2 up to Zn take 1 plus conjugate of Zn, case n equals 2. I'll just come down here a bit. Okay, and then this one is the previous one plus this one, and using case n equals n take 1. Okay, therefore we would say therefore true for all n greater than or equal to 2 by the process of mathematical induction. That ties the whole thing up. Okay, do you get it? You must establish a pattern and show that it flows on. This part here is not deemed to be necessary in this course, but you must make the final statement. That one is that one by continuing the inductive process. That's very, very important. You must be able to indicate that pattern. And you might even put up here, the pattern continues, if you like, if you feel you've shown it. But again, that's not absolutely necessary there. It must be clear from your working. All right, time for you to have a go. So I'm going to leave one here for you and then show you after you've had a go. Prove. Okay, the product, because we've looked at this already, conjugate of the product of n complex numbers is the product of their conjugates. Okay, for all n greater than or equal to 2. That's what you need to prove. So what I want you to do now is to pause the presentation. Maybe you have to toggle back and have a look at the steps, establishing a pattern that you can show will roll on for all n. Okay, pause it and have a go. Right, I'm going to go on now, and here's the proof. So we've got to establish the case n equals 2, because that's where it's said to have started. So let Z1 equal A plus BI, Z2 is C plus DI. So the product is A plus BI by C plus DI. This is all done earlier as an example, wasn't it? So it's A by C plus A by DI, B by C plus CI, and plus BDI squared, which is neg BD. So this is AC take BD plus AD plus BCI, real and imaginary parts. Now let's take the conjugate of it, which is AC take BD take AD plus BCI. Alright, let's now look at the product of the conjugates. Z1 by Z2. Conjugate of Z1 is A take BI. Conjugate of Z2 is C take DI. And the product, here we go, AC take ADI take BCI. We've got to be careful here, plus BDI squared, which is neg BD, so it's AC take BD. Then we'll put the negative out the front and factor these terms, AD plus BCI. Just make sure here you've got that sign. I mentioned that in an example they gave us earlier, because a negative times a positive is a negative there, so you're factoring out that negative. So what have we got here? If you compare these two lines, you can see that they are identical. So the product of the conjugates is the conjugate of the product, and you could put as required there. Therefore, true for case n equals 2. So we have established it for that case. Now let's go on and have a look and label your work. Case n equals 3. So it is the product here, and we've got to prove that it's going to be true by flowing on with a pattern. So let's call this Z1 by Z2, that's one complex number by the other, and we can say therefore it's the conjugate of that product, that one by this one. So you're allowed to split two complex numbers, that's case n equals 2, which we have established. So let's go down here, give ourselves a bit more room, and then we can do it again. That splitting is again case n equals 2, done twice in that example. Now we have established a pattern of process, and so we must repeat that inductive step. We've got to try and duplicate this and show it flows on. So let's go to case n equals 4, Z2, Z3, Z4, using exactly the same pattern, Z1, Z2, Z3, show it's a 2, which can be done as splitting the 2, because we established that with our formal strict proof at the beginning. Okay, case n equals 2. And then, of course, we'll pinch this from here and say we've already established that, and that's going to therefore roll on, and that's case n equals 3. Okay, so we've done two inductive steps there. So, oops, I've missed it again. Therefore, true for case n equals 3. And down here, I like to put true for case n equals 4. And to establish the pattern, I believe you should do one more now. So let's have a look. Come down a bit. Okay, so case n equals 5. So do a couple of inductive steps here. Z1, Z2 up to 5. And what we're going to do is Z1, Z2, Z3, Z4 as a 2 by Z5. Same pattern again, Z1 by Z2 by Z3 by Z4. You're allowed to split those. That's case n equals 2, and it's the same inductive step each time. Equals conjugate of Z1, Z2, Z3, Z4 by Z5, and splitting that now is the previous case, case n equals 4. Therefore true for case n equals 5. Now we've established a pattern, and so we would say continuing the inductive process, because we've got that inductive step always the same. Oops, inductive, I'm saying step, inductive process. We would say the conjugate of Z1 up to Zn would equal Z1 up to the one before n, which is that, which we can split. Alright, there's the inductive step again, times that one, case n equals 2, which is therefore equal to conjugate of Z up to conjugate of Zn take 1 times Zn, preceding case, case n equals n take 1. Okay, so what can we say therefore? Therefore, proposition true for all n greater than or equal to 2 by the process of mathematical induction. Okay. How did you go with that? Okay, so all those steps and these comments and showing the pattern by the same process over and over, so the pattern rolls on, is a very important part of this proof. All right, so you've learned something new there. I hope you can study that and remember that. We'll be revisiting that in other topics in the subject where we need to do proofs. All right, getting a bit heavy there. Concentrate on it, talk to your teacher and other students about it. But for me now, it's cheers, and I'll catch you in a further presentation.